who is recently passed away, and he made a very good contribution in my research. And after 1 year of my MS, I visited him in IIT Bombay, and we had a very fruitful conversation and very good research meetings there as well. So yeah, so this is all about. This is some example of the graphs, and this is not infinity and not a self loop with one vertex. And indeed, we won't allow self loop or we won't. We may allow multiple edges. Okay, let's start with the top. This is a graph. We call this graph as a HF. And start with the definition of perfect matching. A perfect matching is set of blue edges such that if you consider any vertex, there is exactly one blue edge incident on it. So this is a formal definition of perfect matching. And matching curve graph. A non-trivial graph is a matching curve if it is a connected and each edge belongs to the perfect matching. There is a lot of literature on the matching curve graph. It is also known as a one extendable graph when each edge extends to the perfect matching. And now we can generalize the definition of one extendable to the k extendable, where a matching curve graph in which the each perfect matching of size k, each matching of size k can extend to the perfect matching of the graph. Yeah. So this is one motivation to give a name of a cycle extendable graph, and let's see what the definition of cycle extendable graph. Yeah, if you consider edge, now you can find a perfect matching which contains this edge. So now you fix one edge and then you can extend that edge to the perfect matching. Some other perfect matching might not have. Yes. Now in the k extendable, we are fixing first matching of cardinality k, and then we'll extend it to the perfect matching of the graph.
The nontrivial graph needs
at least one edge. Yeah, not real in the sense of at least one edge.
Is this k fixed or is it up to k? Well, I understand that you're fixing this k as a subset of size k.
Yes.
What it is up to k? 1 to k.
1 to k. We can now. Okay.
Have any literature on that? You understand my question, right? So you fix your k. So when k is equal to 1, it's 1 extendable. So when k is equal to 2, it's 2 extendable. I'm asking up to k.
Not aware of that class. Yeah. Yes. Okay. So yeah, this we won't talk about k extendable graph in this talk. This is just one motivation to give a cycle extendable name. We'll see why it is. So a matching curve graph G is a cycle extendable if for each even cycle, so even cycle has a 2 perfect matching. Now we can extend either of the perfect matching of that cycle to the perfect matching of the graph. That's why we call as a cycle extendable graph. And equivalently saying that the graph after removing the vertices of the C has a perfect matching. Yeah, and equivalently C is symmetric difference of 2 perfect matching. And the fourth equivalent, we require a decomposition theory. Beforehand, let's try to see this graph is cycle extendable or not by the definition. So if not, you have to give me a cycle such that after deleting the vertices of that cycle, remaining graph does not have a perfect matching. So yeah, so if this graph is not cycle extendable, you have to give me a one even cycle such that after removing vertices of that cycle, remaining graph does not have perfect matching. So we are deleting the vertices of that cycle, so remaining graph should not have perfect matching. So if you look carefully, this cycle, 6 cycle, if you remove the vertices of that 6 cycle, will remain with the 2 isolated vertex. So this graph is not cycle extendable.
What about odd cycles?
Yeah, odd cycle does not have perfect matching. So
it's only a part of it, right? I mean, odd cycle does not constitute an entire graph. It's only a part. I can have a graph that has a perfect matching, but I can also have an odd cycle in it, right?
Yes. So here, what we are talking about, that we are taking an even cycle and perfect matching of the even cycle, and then we are fixing perfect matching of even cycle, and we are trying to extend to the
No, I understand this.
Yeah.
But I'm asking why we don't consider odd cycles, not with odd cycle.
So one you will get to know odd cycle is not conformal. Like what the conformal is, it will come next. But like we'll in the matching
So
theory,
there's some difficulty.
Graphs with odd cycle is not a problem, right? This is any matching covered graph. There could be odd cycles. The property is about even cycles.
No, that's what I'm saying. Why we don't study properties with odd cycles? Why you concentrate only on even cycles when you talk about that?
Because we are talking about extending a perfect matching. An odd cycle doesn't have a perfect matching. So there's no question about extending a perfect matching.
Okay, so you already have a perfect matching in
yes,
a cycle.
of an even
So you
cycle.
think of
Yes.
that. Okay.
Also, if you remove an odd cycle, the remaining number of vertices
Vertices is
odd.
odd.
Okay.
Yeah. So yeah, so this graph is not cycle extendable. What about this class of graph? What is this graph? Is this cycle extendable or not? Yeah. Since I give you one example of non-cycle extendable, this graph can be cycle extendable, and it is indeed true. This graph is cycle extendable.
You're leaving this homework here. Huh?
Yeah, so it's a really less number of vertices. We can check each even cycle is we can after removing that vertices has a perfect matching. So it's like easy to check in this graph. Before going further, we need one more definition. A subgraph H of a graph G is conformal if after removing the vertices of H has a perfect matching in the remaining graph. And by this definition, we can change our first definition that each even cycle is conformal. So we see four equivalent definition. Let's try to define our problem statement. What is our problem statement? To characterize cycle extendable graph. If we see this problem in terms of decision problem, given a matching chord graph G, decide whether G is cycle extendable or not. And let's ask this question: is it belong to co-entity? That means it is easy to convince your friend that the given matching chord graph G is cycle extendable or not. So yeah, like is convincing your friend that graph is not cycle extendable, you have to just give a one cycle which is not conformal. What about NP? Is it easy to convince your friend this graph is cycle extendable? Just looking at the definition is not easy because the graph can have exponentially many cycles and we have to check every cycle is conformal or not.
You mean every even cycle?
Yeah, every even cycle is conformal or not. Okay, we'll see fourth equivalence. For that, year decomposition theory is required. We'll see what is year decomposition theory. First, what is year? Adding an year to the graph H is consider a two vertices U and V and add an odd path to H whose a disjoint except its endpoint. Where U and V belong to H, apart from that, it is a disjoint from the graph and it's the odd path. It's called as adding a single year to the graph. And what is adding a double year? Consider a four vertices W, X, U and V and add two single years simultaneously. So this is calling a single and double year to the graph. We'll see one example. So consider this graph. We are looking this graph from the slide number 1. So observe that this cycle is a conformal in graph G. That means if you delete the vertices of this cycle in G, you have a perfect match.
there should be odd path. Right?
Yes, odd path. It's an odd path. Now let's add in single year to graph. So this graph is also conformal. The subgraph is also conformal in G and is also matching curve. And now observe that we remain with the two edges E and F, and one can easily see if you either add E or F, the remaining graph you get is not matching covered. So for getting matching curve graph, we have to add E and F simultaneously. So that's called adding a double layer to the graph. And whatever the sequence we show, that's called as an ear decomposition sequence of a graph. That means a sequence of conformal matching curve subgraph G0 to GR such that G0 is a conformal cycle, GI plus 1 is obtained from GI by adding single or a double layer, and the last graph, of course, our graph G. And the question, so we show one ear decomposition sequence for H8, which is matching curve graph. And the question is every matching curve graph has a ear decomposition sequence? And the answer given by Lovász and Plummer in 1987 that each conformal cycle of a matching chord graph can extend to the Hetyei decomposition object, and which gives our fourth equivalent definition. Since each even cycle in cycle extendable graph is conformal, now each even cycle can extend the Hetyei decomposition object. Yeah. Okay. So problem statement which we are looking on and what we already know. A bipartite planar cycle extendable graph characterization. We already known from 2004. Claw-free planar cycle extendable graph from 2020 and claw-free cycle extendable graph from 2022. And our key contribution to characterization of planar cycle extendable graphs in terms of K2 and 4 infinite family, which is generalization result of first two. And H8, as I said earlier, this graph is cycle extendable. It's going to belong to one of our family. So next we will show a brief overview of our approach. Okay. So currently we are looking all planar cycle extendable graph in a matching chord graph. So it is a very wide class of graphs. For an example, two connected three regular graphs are all matching chord. So now we have to somehow reduce our search space to find planar cycle extendable graphs. So let's see, we will first reduce our search space. A parallel reduction. Let E and E dash are the parallel edges. I said earlier, parallel edges we are allowed. Now, if we remove one parallel edge, now we can see graph G is cycle extendable if and only if graph H is cycle extendable. Yeah. Now let's be a series reduction. Consider a path of length 3 whose internal vertices are degree 2. Now we can change this path with the single edge and we can say the same graph G is cycle extendable if and only if graph H is cycle extendable.
This you do only for induced paths.
Induced path, like U and V can have multiple edges, but W and X can be a degree, should be degree 2 vertex. So now we'll say graph is irreducible. So it either of the operation are not possible. That means graph is a simple, say parallel reduction not possible, and degree 2 vertex is a stable set. That means the series reduction is not possible. And the following proposition we just show that let G be a matching chord graph and H be an irreducible graph which is obtained from G by repeatedly doing series and parallel reduction. Graph G is cycle extendable if and only if graph H is cycle extendable. So now it suffices to characterize irreducible matching chord graph. Yeah. Okay. It turns out from here that there is another matching theory implication of cycle extendability. For that I need tight cut decomposition theory. But remember we will go to one another cycle extendable search space reduction one more time. Beforehand, let's see what is tight cut decomposition. What is cut? Partition the vertices of the graph into the two x and x bar. Cut is a set of all edges whose one end in x and another end in x bar. For example, the set of edges which in the blue line we denoted as a parcel of x are the cut. And this is in this example, these three edges are forms a cut. And operation cut contraction, that means we can shrink all the vertices of x into the single vertex. Similarly, we can shrink all the vertices of x bar in the single vertex. For the given cut, the cut contraction, one graph we will get this graph where we did the contraction on this vertex. And if you do another contraction, you will get a K4. Well, complete graph on 4 vertices. Okay. So this operation called as a cut contraction. Yeah. So let's see now what is a tight cut. A parcel X is a tight cut such that for each perfect matching M, it will cut will intersect with the perfect matching exactly one. Is called as a tight cut, and size of x and x bar is at least 3. So we are not allowing a single vertex on x and x bar, and using a definition first point, 2 cannot be possible. Size of x and x bar 2 cannot be possible. So at least 3 on the both sides. And one can easily see by given a tight cut of a matching curve graph, both cut contraction is also matching curve, and it is indeed smaller matching curve graph. Now, once you do a tight cut contraction, you will get a 2 smaller matching curve graph, and we ask the question: is there any tight cut in either of them? If it is, we can repeat this procedure one more time and get more smaller matching curve graph. And we can repeat this procedure until we'll get a graph which are free from tight cuts. List of graphs which are free from tight cuts. So in this example, this is also matching cut graph, and this is a tight cut for the graph. We did a tight cut contraction. In a one part we get a K4, another part we get this graph. And if you observe this graph carefully, this is also tight cut of the graph. And if you do tight cut contraction, you will get one side as a K33, complete biquadrate graph on the 6 vertices. K33, and another side you will get K4 as it.
About this particular picture, right?
Yes, this particular. So this graph, first we did a tight cut contraction. We'll get first this graph and this graph. We have a one more tight cut, and we did one more time a tight cut contraction. We got this. Observe, like one can easily see that these 3 graphs are free from tight cuts. There is no tight cut anymore in this.
So when you're talking about every perfect matching M, so that perfect matching is in your original graph or after contraction?
No, in original graph. So for a definition of tight cut is in original graph. For a given tight cut, but both cut contraction we will talking about. Okay. So now the question is, I gave a one matching curve graph to person A and the same matching curve graph to person B, and they both did tight cut decomposition procedure, which we just now did independently. Means they won't look each other how they are doing. And person A will get some list of graph which are free from tight cuts, and person B also will get some list of graph which are free from tight cuts. Is there any relation between this? Beforehand, we need one more definition. We're saying that a matching curve graph is free from tight cut, is a brace if it is bipartite, otherwise it is a brick. I will note that definition. We'll read it. Matching curve graph is free from tight cut. Brace if bipartite, otherwise.
I think you should remove the is before free, which is confusing.
Okay. So now what I question asked earlier, that person A will got some list of brick and braces after doing tight cut decomposition. Person B will get some list of braces, brick and braces after doing tight cut decomposition. Is there any relation? And the question asked by Lovász and given answer in 1987, that any 2 application of tight cut decomposition procedure has yield same list of brick and braces up to multiplicity of edges. That means if you consider list of brick and braces, person A will get and take a underlying simple graph, and same you will do for the person B, the list are same.
You're doing what? That you are
Yes, it can happen. It can happen.
So which means that you are going to decompose them again and again
Exactly,
till you
that-
reach a point. Okay, my question is, what is the directory that you're going to the point where it does not have a tight cut, number 1? And number 2 is, if at all it's going to reach a point where it does not have a tight cut, how many decompositions you have to do?
So there is, for a given matching curve graph, you can reach always the procedure where we'll get a list of graphs which are free from tight curve. And
So that is guaranteed.
yeah, that is
You're
guaranteed.
always going to do that.
Yes.
So, you know the number of decompositions that you should do based on the properties of or something like that.
So cut can be exponentially many.
See, you're doing a procedure, you're applying something,
Yeah.
and you're expecting something.
Mm.
There's no guarantee that you're going to get that. So
Yeah.
that itself is a property based on the graph.
Can you explain why it will stop? Why will it stop? It
So-
will
See, you're doing a iterative procedure. So I just want to know whether this iterative procedure will stop.
Yeah.
If it does, why? And how many such iterative procedures you have to do? If you know for sure that it's going to stop somewhere.
So how many? So it will stop.
You
That is,
understand the
yes, I
concept?
understand. So that procedure will stop because graph can have, so graph having a cuts, and some cuts
So it's finite, so it's going to stop somewhere.
stop sometime, right?
But
So-
what's the guarantee that all these decompositions, so you're going to have, let's say, 10 decompositions or I don't know,
50 decompositions,
whatever. So all these decompositions are free of tight cuts. What
Yes.
is the guarantee that all of them?
So now we can check for the graph that are free from tight cut or not. That is an easy property. Like
Every time they are getting two smaller
Two
graphs,
smaller graphs.
therefore it stops.
Yeah, I know, but I'm asking whether you have any property based on the graph where you
Yes, yes. So
say
we
that
will
the
say some.
graph has this property, it's going to stop at this point.
So we'll see free from tight cut graph is a brace or a brick. So one can say graph is a brace or brick in a polynomial type. Yeah, brace brace means free from tight cut, which indeed a bipartite. But one can check there is equivalent definitions of brace, and there is another equivalent definition we'll see in a future slide for a brick. So you can check graph is a brick or brace in a polynomial type, and if not, then there will be a tight cut.
That can also be found in.
Yeah, then that can also be found in polytype.
So because you're already taking the graph free of tight cut. I'm asking, check whether it is free of tight cut.
Yes. So that is
We are going to
so.
use this to do that.
So either it will be bipartite or a non-bipartite. Then it will be either a brace or a brick. By checking either it is brace or a brick, we can do in polynomial type.
Okay, okay. That you're going to do.
So yeah, so this is what it says, like for a matching curve graph, a tight cut decomposition procedure for any two application will same list of brick and braces up to multiplicity of area. This is one of the groundbreaking result in the matching theory. It have a several implication. Some of the implication we'll see in the next slide. So it says invariant of number of bricks of a matching curve graph G is the invariant. We'll denote as a B of G. B of G. Barabar. And B dash of G is a number of braces of a matching curve graph G. We require B of G more in this talk. Like B dash of G, just I introduce. So, since we introduce a brace. So one can easily see a matching curve graph is bipartite if and only we'll get a zero number of bricks in the tight cut decomposition procedure. And the next question is, this is an example of a bipartite graph with the blue is a tight cut. And the question is this class of graph where we'll get a tight in the tight cut decomposition number of braces are zero are well known. It turns out that is also a very known class of graph is called as a bicritical graph. A matching curve graph G is a bicritical if it has at least 4 vertices and for any pair U and V, after removing U and V in the graph has a perfect matching. This is an example of a bicritical graph. If you consider a tight cut decomposition procedure of this graph, you will get 2K4 with the multiple edges. And a matching curve graph is a bicritical if and only we will get a number of braces in the tight cut decomposition is 0. So yeah, So one of the theorem proved by Edmund Lovász and Plummer, graph is a brick if and only if it is 3 connected and bicycle. Now we can check in polynomial time that graph is a brick or not. Yeah. Okay. We'll require one more definition called as a graph is a near brick. A matching graph such that you will get number of bricks in the decomposition procedure is exactly 1. So graph is near brick. Exactly 1. For a matching cover. So yeah. So this is the example of a brick, which is a Peterson graph. This example of a near brick, where you will get one K4 and one K33. So these both are called as a near brick. A brick is also a near brick. And this is an example of not near brick graph, where you will get 2 K4, where B of G is equal to 2. Now, which I said earlier, we will say matching theoretic implication of a cycle extendability. We will reduce our search space further, where we require B of G.
So you consider your decomposition as a multi-set?
Multi-set. Yes, it can have a multi-set.
What is the significance of P of G equal to 1? Why not P?
Yeah. So it's like a special kind of graph, and like we gave a
The
name.
significance is coming up.
Yeah, it will come. Like why we talking about near brick? Yeah, like Carvalho and Little proved in 2008 that for a matching graph G, if B of G is at least 2, then there exists an even cycle which is not conformal, which directly implies every cycle extendable graph is either bipartite or a near brick. So now it remains to characterize bipartite and the near brick cycle extendable graphs, and we reduce to irreducible graph as well. So irreducible, bipartite, and near bricks. Okay, we find some of the facts useful that bricks and braces are 3 connected, except K2 star and C4 star. K2 with the multiple edges and C4 with the multiple edges. We saw bricks are all like we see bricks and 3 connected. Now braces are also 3 connected. For a cycle extendable graph and a tight cut, both tight cut contraction are also cycle extendable, which directly implies each brick and braces are also cycle extendable. And only planar cycle extendable braces are K2 star and C4 star. One thing we can remark from here, except last point, whatever we proved till now, it is general for all cycle extendable graphs.
I mean, whatever you present.
Yeah. So from now onwards, we'll talk about planarity, and we'll see why planarity is crucial to get our result. Okay, let's see. So from here we see our proving characterization in 2 parts: minimum degree 3 and minimum degree 2. First, we will see minimum degree 3, which imply brick, and we'll do the brick characterization. Let theorem, which we proved, let a simple planar matching graph with the minimum degree at least 3, then G is a brick. Cycle extendable. G is a planar cycle extendable graph, minimum degree 3, and G is a brick. Proof. We saw that graph cannot be bipartite using the result of Chatran, Kaugar's, and Lick. But now we can suppose G is non-bipartite. We saw that G is near brick by just our previous result. We saw. Okay. Now, suppose to the contrary, G is not a brick. That means there exists a tight cut. Okay. So, let's say there exists tight cut when we take 2 tight cut contraction. We shrink all vertices of x bar into the little x bar, and another we shrink all the vertices of x into the little x. We call this graph as a G1, and this is G2. Now one can easily observe that B of G1 will be like one of the graph in the tight cut contraction having number of brick is 0, and another graph has number of bricks is exactly 1 because our graph is near B. So without loss of generality, we can say B of G1 is 0. That means this graph is bipartite. Suppose this graph is not a brace, that means there exists a tight cut in G1. One can easily see same set of edges are forms a tight cut in G as well. And we can repeat this procedure recursively and can choose a tight cut such that G1 is a brace. And we saw in the previous slide that all brick and braces should be cycle extendable. And the only planar cycle extendable braces are K2 star and C4 star. K2 star cannot be there because of our tight cut definition where X and X bar should be at least 3. So now the only possibility is C4 star. So G1 should look like this, where we did a contraction on X bar, and now vertex V will be interesting in the graph G. So graph G should be look like exactly this. And now that we got a contradiction, since the graph is a simple planar cycle extendable, the vertex V in the graph G has a degree 2.
First make the graph not multi-graph.
No. We'll do tight cut in a multi-graph. Yeah. Okay. So here we got a vertex V which has a degree 2 in graph G, which is giving contradiction that graph G has minimum degree 3. Yeah. Which proves that graph is a. Now we will see the brick characterization. For that we need 2 more things. First we will show that and we'll see that, and then we'll go to the brick characterization. We need a planar cycle extendable implies K2 3 We'll see what is K2 3 first. By subdividing age UV, we can replace age UV with the path of length 3. This is just a reverse operation of our series reduction. And by subdivision of graph is choose any subset of edges and by subdivide each of it. So this is a K2 3 and this by subdivision of K2
mean by subdivide as many times.
as many time you want. Yeah, a matching curve graph G is K2 3 free if G does not have a subgraph that is by subdivision of K2 3. And Gu and Zhang in 2004 proved that for a planar matching curve graph, if it is G cycle extendable, then it is K2 3 free. And we'll try to see this proof. We'll prove the contrapositive. Assume graph is K2 3 base, means it has a by subdivision of K2 3. And since it's planar, consider a planar embedding. So how by subdivision it look like? It will look like this graph H, and it will partition the remaining vertices which is not present in H in F1, phase F1, F2 and F3. Since the number of vertices in by subdivision of K2 3 is odd, the remaining vertex is also odd. So either phase F1, F2 and F3 contains odd number of vertices. At least one will contain odd number of vertices. So without loss of generality, we can consider phase F3 contain odd number of vertices and the cycle which is outer in K2 3 is not conformal because there is no edges from F3 since we consider a planar embedding object. Yeah. So which proves this K2 3 free lemma. We need one more. Mixed bicycle implies K2 3 based in 3 connected graph. What is mixed bicycle? A pair of vertex disjoint simple cycles. Simple cycles we won't allow C2 with the different parities. We'll take a different parity. This odd cycle and even cycle is called as a mixed cycle. And the Paused proved in 2022 that for a 3 connected graph, matching covered is not required here. For a 3 connected graph, G has a mixed bicycle, then this K2 3 based. It's also easy to prove. I will just give you a hint and then it's just working with the mixed bicycle. By Menger's theorem, there exists a 3 vertex disjoint path P1, P2, P3 from whose one end in QO and another end in QE. So consider this two mixed bicycle. By Menger theorem, one can say there exists P1, P2, P3, whose one end in QO and another end in QE. From here, just working around with three paths and two mixed bicycle, you can see easily K23 by subdivision of K23 in the graph. Okay, now we will see, let's try to put everything together and see brick characterization. Whatever we proved till now, we'll see, put everything in and see the brick characterization. Let G be a simple planar brick. G is cycle extendable if and only if G is either wheel or a prism. So what is wheel? Wheel is, consider an odd cycle and introduce one vertex and make it universal. This is a wheel. And what is prism? Consider a two vertex disjoint odd cycle of same parity.
It's same length.
Same length, yeah. And join it with the perfect match. So this is a prism. So this cycle extendable if it is either a wheel or a prism. By seeing definition of wheel and prism, we can easily prove that wheel and prism are cycle extendable. More importantly, forward direction. Suppose G is neither wheel or prism. We'll prove the contrapositive. Then we prove G has a mixed bicycle using the Noren-Thomas brick generation theorem. Then by our mixed bicycle lemma, G is K23 based. And by our K23 free lemma in the planar case, G is not cycle extendable. Yeah, we just see the proof of Brick's characterization. Now we will see the characterization of all planar cycle extendable graph. Let G be an irreducible planar matching graph. What is irreducible? Graph is simple and degree 2 vertices forms a stable set. G is cycle extendable if and only if G is either K2 or belong to our 4 infinite family. Z0, G1, G2 and G3. First I will introduce our 4 infinite family and then we will see the proof sketch of main theorem as well. For introducing, I need one more family which is a bipartite planar cycle extendable family called as a half biwheel. Consider a UV even length path, introduce one vertex H and make it adjacent with all black vertices in the path. We say UV is a corner of the half biwheel and H is a hub of the half biwheel. So this is another smaller member of half biwheel which is C4 and this is smallest member of our half biwheel K2. So let's introduce our all 4 infinite family where G0 is also called a generalization of prism. We'll see why is generalization of prism. Consider a K half biwheel. K is odd and K is at least 3 and orient itself either upward facing or a downward facing and join the edges in the particular manner. And if you consider all half biwheel is a K2 which is our smallest member, then the resultant graph is prism. Now generalized wheel. Consider K half biwheel where K is at least 3 and K is odd. Identify all of its hub into the one vertex and add the edges in the obvious manner. Same, if you consider all half biwheel is K2, then resultant graph is wheel. Okay. Other two family, double half biwheel. Consider a 2 half biwheel. Neither of them we allowed as a K2, smallest member, and add all 4 family or 4 edges in this following manner. So we are not allowing K2 because if we allow K2, it will intersect with the either of the before family. So we want all family will be disjoint. So that's why we are not allowing K2. So last, hexagonal half biwheel. As name suggests, consider one hexagon cycle of length 6, one half biwheel, and add following 4 edges. And if we say half biwheel is K2, then resultant graph is H8, which we are showing from the slide number 1. Okay. We'll see the main theorem proof sketch. Let G be a reducible planar matching graph G. C is cycle extendable if and only either it is K2 or belong to all four infinite family. As always, reverse direction is easy. By just seeing that family, we can prove all members are cycle-extendable. Main result is forward direction. We'll do an induction on number of edges. Our base case, minimum degree 3, which we proved it will be brick, and then we see brick characterization, either a wheel or a prism. That's why it's belong to our family, G0, Z1. Next goal is induction step. So let G we have a minimum degree 2. Consider vertex x0, which is vertex of degree 2, and we'll obtain graph G by contracting vertex x0. What is contraction? Consider a vertex x0 of degree 2. Can both of neighbor called as x1 and x2. It can have common neighbor and other edges. And contract all of both adjacent edges of x0 into the vertex called as x. Can have parallel edges since it have a common neighbor. This is called as a bi-contracting vertex.
Can be put 6.
Yes, 6. All edges. Is called as a bi-contraction. And what is bi-splitting? It's just a reverse operation of bi-contraction. Replace this one vertex with the path of length 2 and distribute all the edges at least 2 here and remaining wherever you want. Observe that bi-contraction is a unique operation while bi-splitting is not unique operation. Okay. So let J star be obtained from G by contracting vertex x0. We'll consider underlying simple graph of J star. So J star can have parallel edge, but we throw away all the parallel edge and we consider an underlying simple graph. We prove that G is also irreducible planar cycle-extendable graph. Planar and cycle-extendable is easy to see. Irreducible needs some work, but which we proved. Now by induction hypothesis, we can say J is either K2 or belong to our 4 infinite family. And now what from here, what we have to do, we have to get from J to G by splitting a vertex. So we proved that J star has at most 2 parallel edges. It cannot have too much parallel edges. In general, it can have too much parallel edges, but what we proved that J star has at most 2 parallel edges. From now, in J, either we have to add an edge, and without adding an edge, we will do by split. So how J and J star is? J is exactly J star, or we got J star by deleting just one edge. And conversely, we obtain G from J by quasi by splitting. What is quasi by splitting? We'll do direct by split, or we'll add one edge and we'll do by split.
You mean add parallel.
Add parallel edge. That's called as a quasi by splitting. And the next goal is to distinguish between good and bad quasi by splitting. What is good quasi by splitting? We'll get a cycle extendable graph in the good quasi by splitting, and in bad we'll get a non-cycle extendable graph.
This addition of parallel edge can be done anyway.
Yes, anyway. Okay, let's see the example of good and bad quasi by splitting. Consider a graph G. We take from generalized wheel family and take a parallel edge E, and now we will bisplit the vertex X. So there is the only way to bisplit this vertex X to get planar simple graph in this following manner. And does this graph is a cycle extendable? That means is the example of good quasi bisplitting or bad one. Since I give a name good quasi bisplitting, it's good one. So this is belonging to our family G2, and so that's why it's a cycle extendable graph.
So G2 is double half.
Double half by wheel family. So this 2 color code is saying 2 half by wheels, and we add 4 edges. Let's see another example. So let's consider the same graph. Now we will bisplit the vertex X without adding any parallel edge. So there is a 2 way to bisplit vertex X to get planar graph. One way is this. We bisplit the vertex X in x1, x0 and x2. This graph is cycle extendable since I give good and bad both. this graph we are seeing from slide number 1 is H8. So belong to our family, hexagon half-life. And another way to bisplit is this one. Obviously, this is not good quasi bisplitting. Can anyone see non-conformal cycle? So yes, this is not conformal cycle. If you delete the vertices of this cycle, you will get x0 as an isolated vertex. So now we start with the cycle extendable graph. We did bisplit and we got a non-cycle extendable graph. Is there anything special about this set of edges in J? If you look carefully, it looks like some good creature. Since it is a two cycle of same parity, shares only one vertex. And we have a name of this kind of cycles. And for the all bad quasi bisplitting, we shows that there exists this kind of cycle in the graph, and we destroy both of them to get a special kind of cycle which will isolate the vertex x0. We'll see in the next slide. We'll call as oscillating bicycle. A bicycle of the Q and Q is a cycle of the same parity which shares only one vertex. And if we do a particular bisplit, we saw in the previous slide, then we'll get same set of edges union Q and Q prime which isolate the vertex x0. This is our oscillating bicycle lemma. Let G be a graph, x0 is a vertex of degree 2, J star obtained from G by Y contracting a vertex x0. And if J star has oscillating bicycle, such that neither Q or Q prime is a cycle in G. That means for all the set of edges of Q could not form a cycle in G. All the set of edges in Q prime also not form the cycle in G. Then Q and Q union Q prime, set of edges of Q union Q prime is a x0 isolating cycle, which is a special kind of non-conformal cycle.
What happens if they have one more cycle attached to it?
No, you don't care, like
Doesn't matter.
doesn't matter. So we found all the bad bisplitting will have this kind of cycles. So this gives the characterization. All good one will give you our family member, and all bad one having this kind of cycle. This ends up the proof. To summarize, we have a cycle extendable graph definition, and we proved this is the main result. I changed the first definition deliberately with at least one perfect matching, since I have some more results and some more graph classes which I explore near to cycle extendable.
So just before we move on, 5 more minutes or 10? 5 more minutes. So probably you can fasten up the next part,
Yeah.
and then spend a bit more time on the K2
Sure. So let's see. The two more graph classes. One is a cycle extendable. Another is called as a PM compact. What is PM compact graph? For each even cycle, after removing the vertices of the cycle, has at most one perfect matching. Which also equivalently say that the symmetric difference of any two perfect matching has exactly one even cycle. And the original definition of PM compact graph arises from polytop, that one skeleton of a perfect matching polytop is a complete graph. Yeah. So we saw at least one here, at most one here. We need actually graph theoretic argument. At least one here, at most one here. What about exactly one? Is this well-known class of graph? And it's turned out there is also class called as a cycle force. For each even cycle, after removing the vertices of C, has exactly one perfect match. And from this slide, you can directly observe that cycle force is the intersection of cycle extendable and the PM compact. Interestingly, people work all three classes of graph independently, but didn't observe this observation. And that is one example. This is a cycle extendable graph, intersection cycle force, PM compact. There is also matching graph which are not cycle extendable, not PM compact. The corollary we just now saw. So we have a result in there is a reason why I introduced cycle force graph. I have a result in cycle force as well. Due to time, I will skip it. So in terms of is a year decomposition, I will I will try to skip it. So in the equivalence of bipartite matching curve graph, which is proved by Gu and Zheng in 2004, having that G is planar cycle extendable, if and only G is K2 3 free. Forgot second definition. That means in terms of bipartite graph, planar cycle extendable graph class is a coincide with the K23 graph class. So what is K23? A matching curve graph G is K23 that does not belong by subdivision of K23. So in the planar graph, the cycle extendable, bipartite and K23 is coincide, and it is here all the members are non-bipartite. So this is one example of a not cycle extendable graph, which is K23 free. So you can see this thick cycle which is not conformal. And in the all graph, these two graph classes are not related, which leads to another open problem to characterize all K23 free graphs. And we have some result in K23 free. We characterize all three connected, irregular and bicritical graphs. All three cases. One I will show you three connected K23 free graph. Let G be a three connected matching curve graph. These K23 free, this either wheel or a prism or a Mobius ladder. What is a Mobius ladder? Consider a cycle of 4K. And join antipodals. This is a prism, Mobius ladder. As usual, our reverse direction is easy once we know the definition of all four, and one can easily prove that is K23 free. Main result is to prove forward direction. Suppose G is K23 free. If G, then we proved it cannot be bipartite by using a Gu and Zhang result from 2004. Now suppose G is a brick. Then we proved G is either a wheel or a prism or a Mobius ladder using a Noren-Thomas brick generation theorem. Now suppose for the contrary G is not a brick. Then we proved G has a mixed bicycle using tight cut decomposition theory, and which implies G is K23 base in case of three connected graph using our mixed bicycle lemma, which is a contradiction. We start with the K23 free, we got a K23 case. So the only graphs are in the three connected case are a wheel or prism or a Mobius ladder, which are K23.
You are assuming in your tight decomposition that the graph is planar.
No. So there is two more result. I won't present all, like I can the proof of this. For a two connected irregular graph is equivalent to say that matching curved irregular graph is K23 free if and only if either a V, either a prism or a Mobius ladder. And in the bicritical case, K23 free graph is either a wheel or a prism or a Mobius ladder. Yeah, which is, to summarize, which is one of the main result is planar cycle extendable graph. And we work around the two other graph classes. One is cycle force. We have characterization of bipartite planar cycle force and characterization of some special cases of K23 free classes, free connected, irregular and bicritical. And we ended up this talk with the one nice conjecture that every K23 free graph is either bipartite or a near brick. In the case of cycle extendable, we got this result using the result of Carvalho and Little. But in the case of K23, it is not having any result till now which we know to say that graph is either bipartite or a near brick. And we have a conjecture on this. We work on this, but we didn't get the result. Yeah. That's it. We have yes. Yes. Yes, sir.
Yeah, this is same as taking a perfect matching of K4 and replacing with 2 by wings.
Yes, same. If you consider both of the half by wheel is K2, you will get K4 in the which is also a wheel.
It's fine the name very double half. That could be the based on K4.
Nice specific way to add this more in this.
Yes, actually, if you see in matching theory, is for if you consider alpha 1 and beta 1, like is a double term. Like if you remove this, the graph is a bipartite matching curve. So its 4 edges are special. That's why I give a name. It will also help us to prove why this graph is cycle extendable.
Related to some social observation.
Yeah.
The 4 edges formed by the union of 2 removable double sets.
Yes.
So is the number of half what you think that
Yeah. In G0 and G1, I will use odd number. Here I will use 2 half by. Yeah. Here I will use at least 3 and odd. Okay.
it's